My notes. So if anyone wants to follow along in the group chat, I've sent through my notes. So if I'm like rushing too quickly through it, you can always just jump back and forth and do it at your own pace. So yeah, welcome to the Solids Crash Course. I'm Henry, and that over there is Prash. And yeah, so we're going to be running this workshop for you. So before we dive into it, I'll just give you a bit of an overview. So if you don't know how I teach, I like to start very general and get more and more specific. This course, right, there's a lot of formulas, especially at the start. The first like 3-4 weeks, it's going to be rough, all right? I'm not going to lie to you. This course starts hard, and I think it gets easier. In contrast, fluids, I think starts okay, and then it gets, it's like a medium, then easy, it gets hard towards the end, all right? But you'll find the right balance. If you want to take notes and stuff, feel free, but otherwise, these notes will be available afterwards too, and the recording will hopefully work. But yeah, anyway, so that's an overview. First, I want to talk about what the point of this course is, right? So the point of this course is it gets you into structural engineering, and it will help for like geotechnical engineering as well. We're going to be focusing on solids, which of course, like contrasted to fluids, is like solid materials, right? It's like yeah, things with like a set shape, a set volume, and what we do with that. And so there's some fundamental theory which we're going to be breaking down in this workshop. And yeah, can I just get a show of hands of who's done maths 1101? About half of you? Okay. I'll try to jump into some of the math stuff, but it does help to have done it first. But don't worry, like I didn't do maths before I did this fucking course, and I was fine. So it's alright. But basically, the main point of this course first is that we're going to be looking at the start at the cross section of like a beam, for example, right? So we're going to be dealing with like geometric properties and stuff, and looking at stress, strain, things like that. But the underlying structural assumption, it's pretty basic, but the underlying structural assumption that you have to be thinking about, well, actually not really in this course, but like in future courses, right? It's going to be about whether your capacity is greater than your loading, or your loading is greater than your capacity. Your capacity being like your structure, how much it's able to take before it breaks. And then the loading being that force or that moment or whatever that's going to cause it to break, right? I'll just go right here. So if your capacity is greater than your loading, right, your structure is stable. Whereas if your capacity is less than your loading, your structure is going to be unstable. So all the stuff that we're going to be talking about in this course will be diving into one side of this assumption or the other, like the capacity side or the loading side. And you'll see how that fits in once you do your like design courses in future years. And the other thing that I'm going to be talking about is Moore's circle. And this is a very notorious topic because yeah, like it comes up in this course and it comes up in soil mechanics. And it's just one of those things that overwhelms you with a bunch of formulas. But like, yeah, I think if you break down like to its core or whatever, like it's basically just circle geometry, like being able to work with the circle shape and yeah. So you got a question? Yeah.
Just a quick question. Do we get a dot shape or a formula shape?
Yeah, really good question. From the course, I think there is, but Clarissa Liu's formula sheet. This is the greatest thing in the world, okay? This is in the folder which I've sent. She's written down every formula. So again, if you look at this and you're like, what the fuck am I looking at? That's normal, that's okay, all right? Each individual thing is gonna make sense after you, like, you either know it or you don't, all right? So the idea is we'll get you over that threshold today, hopefully. You can look at it and be like, okay, that kind of makes sense, all right? That's just week one. Like all the stuff I just showed you is week one. That's week two, all right? So you get the idea. doing a lot of formulas every week, and just going to the lectures alone it's pretty rough. Like you're just going to be bombarded with a bunch of stuff. But you'll notice that there's a lot of overlap. Like what I'm saying, like the Moore circle, that's going to be in week 1, 2, and 3. That's already half your formulas like covered. If you just understand the Moore circle. So yeah, it's not that bad. All right. Yeah. Does anyone else have any more questions before we get into it? Okay. So yeah, and also these topics here. Engineer's beam theory, flexural formula, and deflection. Those are very important components, like outcomes of this course that you'll get as well. But that will be kind of covered from, I think, week 5 onwards, and Prash will be talking about it kind of from a bit more of a theoretical point of view, I believe. Yeah. So he'll cover, yeah, if you haven't deciphered this already, Prash has a lot more experience than I am, and he's got some industry experience and stuff, and he's taught for a while. So he'll be able to tell you it from kind of that very applied point of view. So you can see, like, you know, how those things like play into real life engineering design. All right. So the first thing is capacity and loading. So this is a very basic thing in theory, but yeah, I just want you to think about, for example, here's like an I-beam, right? Steel I-beam. Can anyone think or like tell me about what like gives this like section of the I-beam its strength, and what causes it to fail? I guess like the loading on it, right? So I don't have any like words or guesses to do this.
Is it like tension?
Tension is an example of loading. True. So actually, as a matter of fact, ENGG2400 is the only like kind of mechanics / engineering studies related course that you've kind of done so far, besides maths. But ENGG2400, if you recall, you learned how to calculate these shear force diagrams, right? Maybe it looks something like that. And you learned how to do like the moments, which might look something like that, right? Axial forces act on things like trusses, right? If you remember, there's your tension, your compression, all that stuff. That's all to do with loading. That's all to do with what causes the structure to break, right? So yeah, those would be examples. Can anyone else think of what might give this I-beam its strength, for example? So, symmetry. So it's shape, right? 100% right. So one thing we're going to be talking about is geometric properties. In fact, that's the first week of this course. Would you agree that the shape of this I-beam, if it was, for example, bigger or a different shape, say it was like orientated like 90 degrees, so it's like a H instead, so it would have different properties, right? In bending, or in shear, or or even in tension and compression. Like the shape of it will affect its properties, right? And how much it's able to take. So that's what geometric property is all about. So yeah, there's one more kind of overarching category which I want to touch on here.
Materials.
That's right. So especially if you've done Maths 1101, it's to do with the material properties, right? So let me just write that down. So if you remember, there's like elastic modulus, shear modulus. We'll be talking about these in a bit, so even if you haven't done this course, you'll be fine. If you haven't done maths, right? The material, like this is a steel I-beam potentially, but it could be made out of timber, for example, and they would have different capacities, right? Yeah, and then where this course is going, as well as geometric properties, is we're going to be talking about stress and strain in quite a bit of detail. It's kind of like week 2 and 3 material. Yeah. That's kind of a map of the start of the course. All right, like, yeah. You guys still need a second to copy this down, or? Yeah. All right. Again, the notes are up on in the chat, in the Facebook chat. So if I scroll past, just copy it. Does anyone else have questions for the moment? Oh, okay, cool. So if you actually just show of hands, who was in my ENGG2400 class? Got a couple. So if you were in that class, if you recall around like week 7, in the civil stream of 1300, they talk about geometric properties and stuff, and I talk about this, but this is one of those things they never really explain to you in a specific course. They don't explain to you how to read engineering drawings. Or maybe if you've done the Revit course already, the BIM one, but like, it's just assumed knowledge. Like, so every course is assumed knowledge, assumed knowledge. So I'm going to teach it to you now, because you only need to learn it once and you'll be set for the rest of your degree, right? A perspective drawing is basically like this. It's like using up to 3D, like 3 dimensions, and it's just to give people a better idea of what you're looking at, right? Because humans can interpret like 3D drawings a lot better than like if you only isolate it to 2 dimensions. Here's a plan view. So when I say plan view or top down, it means like bird's eye, right? So looking at it top down, right? And your elevation view is potentially what you see in like a lot of free body diagrams, where the vertical axis is where gravity acts, right? So that's just like side on. Lastly, the cross section. So this is very important for the first week's topic, which is talking about our geometric properties. So here I've used an I-beam as an example, like a steel I-beam. But yeah, remember, we're looking at the cross-sectional area. Yeah. By the way, this is called a prismatic I-beam. It's called prismatic because if you remember like geometry in like year 9, a prism, like a triangular prism, is just, it's stretched across, right? It's the same shape, but just stretched across. So a prismatic I-beam means it's the same shape, but across the whole way, right? Yeah, so this will be geometric properties here. I'm telling you this because when I did this course, I didn't know what I was looking at. I was just like, oh, this is like some shapes and stuff. But it's to do with, it's like, say this is on a beam, right? Yeah, say this is on a beam, then this is why it's important, because when you do steels, when you do concrete, you're going to be analyzing these cross sections of your beams when you're designing it, right? Yeah. Okay. Does anyone have more questions? Or let's move on. Yeah. So here's a perspective drawing, right, of this I-beam. Pretty much the same drawing that we've been doing, and yeah, take a second. So here we have our centroidal axis. So a centroid, right? You're gonna hear this term come up every now and then. You guys all familiar with center of mass? You know, say you have like a balance, like scale or whatever, and you have 2 objects on either end and like the different weights and stuff. It's just the middle of where the weights of like the whole system is, right? That's the center of mass. So our centroid is basically your center of shape, right? So in this case, since it's a symmetrical shape, it's going to be right in the middle, right? So that's our centroidal axis. We're looking at this I-beam here, and actually that's all I mentioned for now. Okay. So finding the centroid, this looks very familiar to center of mass, right? The only thing we've done is we've subbed out what would normally be m here for area. So I'm going to erase that because that might be confusing. That's not referring to meters, that's referring to mass. That's for your center of mass pretty much, but it's a center of area, right? Yeah. And you can do it in the x direction and the y direction. Because that makes sense, right? Because if you have a T-beam, for example, which centroid is going to be in the middle and which one's going to be off center?
Y is going to be off center.
Exactly right, yeah. So your y is going to be like here, it's going to be skewed towards the top because the majority of the shape is above the middle, right? Okay. All good so far? Yeah. So first moment of area won't be as much of a focus in the first weeks of the course, but I think maybe Prash, yeah, it's going to come up later on, so I'll let him talk about it. Just note that it's essentially like taking the moments, like, do you remember in 1300 you take a moment, except instead of a force, you're doing area. So what I mean by that is like, do you remember the moments formula? So this is, you're taking a moment, except instead of force, it's area, right? Again, this isn't immediately obvious what this means, but this is kind of just where it comes from. Don't worry about that for now. Second moment of area, yeah, good question.
I never remember QY. Is that pushing it around the x-axis and then QX pushing it around the y-axis? Is that how to think about it, or is that?
Let me think about that real quick. Okay, so basically, if this is your x-axis, right, and if this is your y centroid offset from it, I believe the first moment of area is flipping it that way. I think so. Prash, that's right. Yeah. He's nodding, so I think we're good. Yeah. So, yeah. In that case, that one is referring to this, right? Is that right? I'll leave that there for now. But yeah. So for second moment of area, this one's going to be the main focus. So there's a few things to break down here. The first one is that it's shape dependent, okay? So this formula, I've only wrote it for the general case of a rectangle, okay? So let's do a T-beam, for example. You can break up this T-beam into two shapes. You can break it up here if you like. You call that shape 1, you call that shape 2. And essentially, this component here is saying you take B as the width, D as the depth of these shapes, and you add them together, okay? So say this is like 50, like 20 or something. This one's like 20, and this one's like 100. Actually, let's not use 20, let's use 30, right? So for this particular shape, you do it for shape 1, right? So this is shape 1 here. So B is 20, and then the depth is 50, right? And then to the power of 3 over 12. So this applies for a rectangle, and you add it onto shape 2, right? That's kind of how it slots in, right? But then you have this part here. Let's highlight it. Sorry, it's gotten a little messy already. This component here is called parallel axis theorem, parallel axis theorem, and it's to do with the offset of the shape, okay? So essentially, if you have a rectangular cross-section like that, and yes, if you have a rectangular cross-section like that, it doesn't have an offset from its total centroid, right? So you don't need that parallel axis theorem shift. But if you were to make it a T-beam, then you have to account for the fact that this gives it additional bending resistance. I should call that this right there. So you can think very generally of second moment of area as bending resistance. We'll get into that a bit more later. But yeah, the offset of where these shapes are will increase its ability to resist bending, right? So that's what parallel axis theorem is accounting for. Yes, but importantly, y hat subscript t, this refers to the centroid of the total shape. So that's what we were talking about before, where the centroid of this total shape is not here, right? It'd be somewhere skewed upwards, so you'd have to find where that is, and then find the shift relative to that point, right? Did you have a question, Roger? Yeah. Hopefully that makes sense. And you'd have to shift both these shapes relative to the centroid. So if the centroid is here, you shift this one to here, the middle of it, and you shift that one to here, the middle of that one, right? It's kind of how you have to think about this formula. So yeah, like this is a formula which is going to take a fair bit of practice, but it's one that you want to get used to because you use it in this course and use it in future courses as well, right? Yeah. Something to note as well, the formulas I've given you are for discrete shapes, right? If you're given the calculus function, you're going to need to use integration to find the area. You can see that in the worked examples, but that comes up less. In general, we just deal with the discrete shapes when we're dealing like in steel structure design and stuff like that. Yep. Something to note as well, IY, this is the moment of inertia, but bending that way. See where my hands are going? So that way instead of that way for a beam. Right, so it's bending side to side like that. So let's just do a quick thought experiment, right? So this is an I-beam, right? So beams are supposed to take these like kind of gravity loads from the top due to gravity and stuff. Would you expect to have a better bending resistance that way or that way? So side to side or up and down?
Up and down.
Up and down, right? So that's what the shape is optimized to do, essentially, right? In fact, you'll find that like these I-beams, they'll take something like 10 times more bending from the XX axis, which is called its major axis, as opposed to its minor axis, right? But yeah, there you go. Any questions to do that? Cool. Let's talk about the product of inertia. So I'm going to call this the balance of area. That's kind of how you want to think about this, as in mathematically, that's how you want to think about this. So essentially, for a rectangle about its centroid, so what I've drawn here is actually a rectangular cross section, right? And then here's this centroid, right? Do you remember your like quadrants from unit circle? You can kind of think of it like that. So for each of these quadrants, that's what the maths for IXY is going to like add or subtract from. So for this shape, it's 0 because they balance each other out. For another shape, an I-beam, for example, would this be positive, negative, or 0? 0 as well, because it still balances itself out, right?
Yeah.
What about for this shape? Maybe that.
Would it be also 0?
Yeah, it's also 0, right? Because this part is positive, and this part's negative, and what I just highlighted will net to 0, right? Here's an example of a shape that isn't 0. Is that going to be positive or negative?
Negative.
It's going to be negative because the positive area is only this. But yeah, there'll be a formula for it. I actually don't think I've included it in these notes, but in Clarissa's formula sheet, there'll be a formula to calculate your what do you call it? Your product of inertia properly. But yeah, that's like right off the bat you can just tell. Okay. And radius of gyration, I'm not going to touch on this too much, partly because I don't know what it is. And yeah, Prash, you can cover for me later on that one. But Mathematically, it's just you have your total ix and iy that you've calculated, and the total area of your shape, and you can figure out the kx and ky from that, right? Yep. It's just like an extra step that I might ask you in like the workshop questions and stuff, but yeah. All right, cool. So we're gonna jump into an example here. I hope I don't run to overtime. Just give a second. So here we have a T-beam. I'm going to call the top shape here 1 and the bottom shape here 2, right? You got this dimensions and everything. So one thing you want to think about is from our, actually no, I'll talk about that in a bit. Okay, so the formula, right? We saw the formula for Ix before. It goes like this. Except what I've written out here is only for shape 1, because we have to add on this formula again for shape 2, right? That's for shape 2. And we have to account for parallel axis theorem. Formula goes like this. I wrote the formula wrong. It's that with a squared. Okay, if you're looking at my notes, I wrote the formula wrong before. It's with the squared pretty much, right? Okay, we're gonna plug in these numbers, okay? Can someone tell me what B is for shape 1? The width?
400.
Correct. What about D? Yeah. What about shape 2? B.
Sorry.
You're right.
About 200.
Yeah, 200. What about D?
300.
Very good.
Is that
All right, what about the area? You don't have to tell me what the area actually is, just what do I multiply together?
100.
Not quite 100. Oh, well, 100 that way, yeah, you're right. And 400, you see?
100.
Yeah, you got it. I was looking at the other dimension, yeah, you're right. Yep, so that's how we sub in the area, right? And then YT. We don't know YT because it's the centroid for the total shape, right? So we actually have to calculate that. But we do know Y1 hat and Y2 hat. And the way we get that is it's based off of the defined axis, right? So it's from the defined axis to the center of that shape. That's how much you have to shift it by, right?
Is the defined axis given to you?
Yep. Like that, right? So from the defined axis to the center of shape 1, what distance would that be? I think. Yep. So 50. What about shape 2?
150.
Thank you. Very good. So that's 50. 150. Okay, for YT, normally I actually do this all the way around, but I just wanted to do this thought experiment, right? We have to calculate YT, right? So that's this formula, right? And so we have two shapes, so we have to account for shape 1 and shape 2 here. We do its y, which was 50, multiplied by its area, plus the y of shape 2. Okay. Alright, so I'll do that later. Just listen up real quick. So, this I've left blank intentionally here. For the centroid, position of the centroid of shape 2, right? What number are we gonna put in there? Sorry.
The R is not.
What number am I going to put in here for shape 2?
Is it because it's below the x-axis?
Right. It's going to be negative. We have to account for that. Otherwise, yeah. Otherwise, we're just going to go up from, like, yeah. This is going to be the wrong number pretty much, right? So you have to remember that this is a negative 150. So remember that's gone down 150, right? And this is going to give me negative 70. So what negative 70 means is we go down from our defined axis by 70, yeah? Yep, and that's going to be where our total centroid for our shape is going to be.
Would that work if the defined axis was literally anywhere else? Like, could you put the defined axis at the bottom and then?
Yep.
Okay.
Because it'll give you the right spot anyway.
Yeah.
It's kind of like a coordinate system. And so what happens with the parallel axis theorem and when it takes it, so I'm going to plug in negative 70 here. The reason why sometimes you might see this formula the other way around, you might see yi minus yt, is because it's squared anyway. So it doesn't matter which way around it is. Yeah, all that matters is
The difference between them.
yeah, like if the defined axis is down here and you find this number instead,
Yeah.
all that matters is the center of the shape to where the
But there'll never be a case in a question where they don't give us the defined axis, right?
never. And I mean, if you're establishing it for yourself, say like you're just doing a thought experiment where you want to find ix for some random shape that you made up for whatever reason.
Okay, yeah.
You can put the defined axis anywhere you want, and if
Even
you
if it's
plug in
like-
the numbers right, yeah, like you should get the same answer no matter what.
Okay.
That's how these formulas have worked out, right?
That's pretty cool.
Yeah, it's like a datum for. Do you remember work energy in like 1300? Doesn't matter where your datum is. Your change of height's gonna result in the same thing, right? Yeah. Anyway.
Okay. Seems pretty real. So like,
Yep.
not making sense. We should make a point.
All right. Can I just get your attention for one more second here? So that gives us, once we plug in all those numbers, that's 14.33 10 to the 8 mm4, right? Okay. Let's let's have a think about yi.
What's the fourth? Why is it millimeters second?
Oh, okay, okay. This is a good question, right? So essentially, for me, it really tripped me out to think about why this is mm to the power of 4, like the units, right? Because you're like, whoa, we're in like the 4th dimension. But it's actually not that. It's just because it's a like a mathematical nuance when you replace all these. So for things like center of mass, right? Or you might have seen this at the end of 1300. Things like that.
Yeah.
It's the moment of inertia of mass, right? A mass moment of inertia.
Yeah.
The units for that were kilogram meters squared. So when you're replacing the mass component with area, that kilogram becomes in terms of m squared, right? So that's why you get m to the 4. You're not working in the 4th dimension. This is just the units that we've replaced for this like theory or whatever to work, right?
Okay.
Okay, yi. Can someone tell me for yi, how are we going to calculate it? Given that we have this formula here for ix, right? What would be different about the y formula?
There's no shift.
There's no shift, correct? What else?
It's
You just take it from other dimension. Correct, correct. But what we're going to do is we're going to shift this 3 onto b, right? So that's going to move over. So same dimensions, but it'll look like this. Right? That's the wrong one. Let me delete that. Sorry. It's this, right? So the b is the component which has the cube, right? And no shift, like you said. So because there's no shift, you don't have to calculate x t hat, right? You don't have to find the total because you know it's right on the yeah, like your defined axis. So there's no shift required. Yeah. Okay. Any questions? I'm gonna have to speed it up a bit so that Prash has more time to speak. But that was, yeah, I'm only 4 pages through my 10 pages here. I'll speed it up a bit. Okay. So we're gonna talk about something that you've probably seen in Maths 1101 if you've done the course before, right? We're gonna start talking about stress and strain, and a little bit about elastic modulus. So when you have a tensile test piece, right? So this is made out of like glass or whatever, and you pull it apart using this tensile force. You can get a few things out of this test, but this would be the cross-sectional area, right? And you'll see that this test piece has this like deformation that you can call delta L, and you can derive these what do you call it? Quantities. Yeah, you derive these quantities from this test. You can get your axial / normal stress, and you get your axial / normal strain. So that's what I've denoted there. So that Greek letter there is sigma. That's also the area. That one there is epsilon, and that's your change in length over your original length, right? That one's unitless because we're doing meters over meters, and pascals is newtons over meters squared, right? Yeah. And elastic modulus is going to be your stress of your strain in your elastic portion of your material. So basically this varies per material, right? Which is why you need to do testing on it. It's a material property, right? So here's an example. So you've got steel, right? This portion here is considered your elastic portion, and here is considered your plastic area. Plastic is where there's irreversible deformation. Like you unstretch it and it's still fucked, pretty much, right? That's what plastic means. And essentially this slope here in the elastic region is your elastic modulus, and you get that from doing stress over strain. At this point is where it's yielded, and this point is your ultimate failure state, right? Anyone have any questions to do with this? No? You'll see elastic modulus pop up starting from about week 4. Yeah, week 4. But it's related to stress and strain, which is why I want to bring it up quickly here. I talked about this a little bit if you were here for the fluids workshop, but your shear modulus is also kind of to do with material properties, right? Except it's looking at different types of forces. So before we were talking about axial forces, such as like tension and compression. Shearing is like parallel to your surface. So it's like your tangential forces, essentially, right? And so the example that I gave the other day was like, imagine we have like a cardboard box, it's full of something heavy, and I'm just like pushing it along the carpet here, right? Applying a force like what's seen on the board here. It's shearing against the ground, and that shear area A, that's going to be the area that you're plugging in. And in terms of deformation, we call that delta X. So that's going to be plugged into your shear strain here. That's shear strain, right? Yeah, and gamma, right? Gamma is an annoying character because maybe in fluids you've seen it pop up as the unit weight, but in solids, yeah, it'll be your shear. It's referring to shear strain, right? Yep, and then you got shear modulus too. Yeah, any questions on this? The only reason I bring this up is because it's going to be relevant when we're talking about the next topic, which is to do with stresses, specifically on a Morse circle. Yeah. Okay. Going to keep going now. I'm going to do a quick question. I really like this question because most of the questions that you're given in the workshop is just the Moore circle stress transformation. You're gonna get really sick of it. But then they chuck a couple of applied kind of questions, and I think you learn a lot from those. So here we've got a beam that's supported by two rods, right? So we call it a rod AB and CD. And the question wants us to find the distance here. I've denoted in lowercase d. This kind of looks like a 1300 question, right? But there's a bit more steps to do with the cross-sectional area. They want us to find the distance d such that the stresses on both the rods are the same, right? So the first thing to note is you can do this in all sorts of units, right? I've solved it in terms of kilonewtons, meters, and kPa, so kilopascals. But if you want, you could do it in terms of newtons, millimeters, MPa. These units really like working with each other. Or you can also do. When you stick with one of these sets of units, you kind of want to carry it through for calculations. Just yeah, but kilonewtons, meters, and kPa, those work really well in like big scale questions in terms of like beams and buildings and stuff like that. Newtons, millimeters, MPa, that's generally what you work with for stresses or like looking at a cross section, smaller scale kind of questions. Yeah. Anyway, so I'm going to be sticking to this one. Okay, so firstly, can someone tell me what the basic formula is for axial stress? Does anyone remember? The one for sigma. Tiara? No, I'm kidding. You were like, don't pick me. Yeah, it's just force over area, right? The sigma is force over area, right? I'm going to call the force in this question tension, T, right? So we're just going to replace that with T. So tension is just stress times area, right? Just rearranged it. Here, because our stresses, we want it to be the same number anyway. I'm going to call the stress in AB and CD just sigma. It's going to be the same thing, right? So the tension in rod AB, right? It's going to be sigma multiplied by the area of AB. That's the thing that's going to change, right? So if you look up here, the area for rod AB is 12. It's 12. Yeah.
Why is it both 12 and 8?
Oh, yep. Sorry, I should have explained that. So rod AB has an area of 12 millimeters squared, but rod CD is a little bit slimmer.
Oh, I thought.
It's got a different area, right? So that's why this question will be like off center. So here, I'm going to convert the units by doing this. You might or might not have seen this before. It's a bit funny, but I'm multiplying by meters squared and dividing by millimeters squared. So I'm going to get meters in the end, right? And there's 1 meter per 1,000 millimeters, right? So basically that gives me this. 1, 2, 3, 4. Right? So that's our area here, right? And then when we multiply it by sigma, we just have our area, which is written like that, multiplied by sigma. Tension in rod CD here, we can do a very similar thing, and end up with 1, 2, 3, 4, 5. Right, done the same thing, just multiplied by sigma, our unknown, right? Here I've drawn a free body diagram, so using like your methods that you learned in engineering mechanics, some of the forces in the y direction. Actually, can someone tell me them? What are the forces do we have in the y direction here? Yep, that's one of them. Yep, basically, right? So I'm just going to add the arrows that I've drawn going up and subtract 6 kilonewtons, right? We're working in kilonewtons here. Here I'm going to replace these with what we worked out. right? So we can work out that sigma, that gives us only one unknown. That's just that many kilopascals, right? Taking the sum of the moments here, we're going to do moments now. So looking at this picture, can someone tell me the sum of the moments about A? So what kind of moments will we have going about this one here?
Minus 6 times d.
Yep. Yep.
Minus tc. Oh, positive tcd times 3.
Yep, basically. So we're just taking the sum of the moments like we did back in 1300. Oh, sorry. We'll solve that d is 1.2 meters, right? Yeah. So that's the question pretty much. Yeah, you.
Doesn't matter what we take the moment from, right? Doesn't
No.
matter which is.
Yeah, you could take it about A or you could take it about C. Let me tell you something which I teach in 1300. You look at basically where your lines of actions are for your unknowns. So we have here and here, like vertically, that's where our unknowns are. So if you take the sum of the moments about this point randomly here, you're going to end up with two unknowns, right? If you take it about A, you're only going to end up with one unknown because the lever arm on one of the unknowns is 0, right? And if you take it about C, yeah, you only have one unknown as well. Yeah. Does it make sense how this is tension, by the way, on the rods? Yeah. Okay. All good? Let's keep trucking. So here, right, oops. Basically, let me introduce you to a 3D stress element here. A stress element is pretty much like, it's like an imaginary thing, right? It's like the smallest unit. Basically, you have like a random point in a structure, and you can look at an individual stress element happening in that point in the structure, right? And then you can analyze that point. So the stress elements is representing pretty much the stresses which are happening at that point. And that, you know, it might not actually look like a cube or whatever, but it's representing it, kind of like how you represent an atom in chemistry or whatever, right? This is actually overkill because we only deal with 2D stress elements. I'm just showing you the 3D version, just to trip you out. But like at the bottom here, I've shown you this kind of like heat map. And this is called finite element modeling. You do a little bit of it in 2303, right, Prash? No? Okay. Well, finite element modeling, you might do if you do like research or something. It's basically where you can find the stress at any given point using like computer simulation on a structure. So this might be some sort of structure or whatever object that you're looking at. And yeah, you can analyze like all the stresses and stuff. So that's what like stress elements might be useful for, right? Caden, does this look familiar?
Yes, it does.
So this, just to give a random example, this is a game on Steam called Polybridge, and it's where you can like build this like truss bridge, and in green is where there's areas of low stress, like low axial stress, and in red is where there's high stress. So this is a perfect nerd engineering game, but it's an example of where, you know, stresses might be used, like, in a, yeah, it's just for fun, you know, just a little fun example. So this is the version that you'll see in this course, right? Plane stress. All right. So the focus in this course. So just keep in mind the directions of all these arrows because it's going to be important when you look at a stress element. So as the positive, alright. So we're looking at the x direction and the y direction here. And when the arrow is pointing away from the center, that's going to be positive. It's like in trusses where you have like tension as a positive direction. For shear, it's going to be pointing in the top right corner and the bottom left corner. Those are the positive directions. If it's pointing in the right way around. If it's pointing in the top left and bottom right, those are the negative directions. Shear. Okay. You have to get pretty familiar with that. In soil mechanics, which a lot of you will be doing in term 3, compression is the positive direction, right? Because, could anyone tell me why that might be for soil?
What's the question?
The question was, if you're analyzing a soil element, right, so like some point, you're analyzing the stress at some point in the soil, why would compression be the positive direction in soil mechanics? Yeah, because like, as like you go deeper and deeper into the earth, right, you're gonna experience, like the soil's gonna experience more compression. Whereas for structure, I guess like tension, that's when like, for example, concrete is quite weak in tension. It's gonna rip apart faster in tension. Yeah, I don't know. I just assume that's the reason. That's what I remember, right? Okay. I don't know, bro. Vibes. Alright, so here might be a typical question in week 2, right? So here I've written down the principal stresses formula. Okay, I'll explain what that is. But this is what the formula looks like. Can someone tell me what I should plug in for these numbers? So sigma x, sigma y, and tau xy. So what do you reckon we'll plug into those numbers?
Sigma x is 9.2.
Sigma x.
15.2.
Oh yeah, true. Yeah, pretty much right.
Yeah.
And then actually I'm looking at so just looking at this, right? What about sigma y?
It says about the negative something.
It's not quite 9.2. Negative 9.2, right?
So that's because it's going to the top left or the bottom right.
We're looking at the arrow, the axial arrow here. And if it's in compression, it's going to be negative, right? That's what you plug into the number.
Yeah. Wait, so will all x shear forces be positive because we're up down?
It's about the corner it's pointing in. So actually in this case here, right? Here it's pointing in the top left and bottom right.
Okay.
So it's going to be negative because that's the negative convention. Whereas if it was pointing in the top right and bottom left, that's the positive direction.
So both of them are negative.
How do I explain this? Like,
But am I looking at the red arrows right now?
oh, the blue arrows.
But all the blue arrows are in the negative direction.
Oh, sorry. Wait. So for tau, you're looking at the blue arrows.
Yeah.
Are they in the negative direction? I mean, we're looking at. Wait, let me redraw it. So these ones are pointing up and left, right? And these ones are pointing down and right. That's the negative direction, essentially, on a stress element.
Wait, no. Dude, never mind. Don't worry about it.
All good.
Wait,
Okay, just take my word for it for now, Caden. I'll tell you later. Okay.
Okay.
So this will be 21, negative 21.1. It's going to be negative because it's pointing in the negative convention direction, right? Yeah. The principal orientation, again, I'll show you what this looks like. It makes more sense on a Moore circle, right? But the principal orientation is, yeah, it has this formula. But this isn't what we're going to be using directly to get the principal angle. Right? So we're going to sub in our numbers as we did before. And then, whatever we got on the right-hand side here, we're going to take the tan inverse, right? We're going to take the tan inverse of whatever we got, and then we're going to divide it by 2. Right? and that's going to give us our principal stress. I'll show you what that looks like on the circle, because the circle is quite good for visualizing what all these equations and stuff are actually like plugging into.
That's the theta is the stress or the angle?
The angle. Okay, so firstly, actually wait, I'll show you on the circle. Wait, is there else? Wait, do you need to copy this down? Sorry.
Yeah.
This is what a question will look like. Okay. From your tests, you know that in the x on the y direction, the stress element is giving 2 MPa in the x stress direction, and it's giving -1 in the y stress direction, right? These are the axial stresses we're talking about. And then for shear, it's giving -0.5, right, in your xy plane, right? But then this question particularly asks for 2 things. They ask one. It asks for 2 things. So the first one is, what will the stresses be when we rotate this element 30 degrees? Okay, that's the first thing. So this is called transformation. Transformation is where you rotate it. And the other one is for the principal stresses and the angle at which the principal stresses occur. So I'll show you what this looks like on a circle. Here I've plotted it. Here I've plotted the xy plane, right? The xy plane is just what happens to be the stresses based on the xy coordinate system, right? So on a Morse circle, that's not necessarily like flat. So the points that we're looking at are here and here, right? Based on the values that were given. And then the red line here, the red line is your principal plane. Your principal plane is always flat on a Morse circle. Your principal planes is basically where the minimum and maximum axial stresses will occur, right? And it will also be where there's no shear stress. So shear stress is 0 on this graph, right? Agree? Okay. And so in terms of circle geometry, right? How, like intuitively, like from guessing, how would you find your principal plane just by looking at a circle? Like, so how would you find these points? We call this sigma 1 and this is sigma 2. Given that we know these points.
What do you mean? Oh, given that. Find the center of the circle and then find the radius.
Exactly. So it's the center of the circle, right?
Yeah.
Plus or minus the radius of the circle, right? That's what the formula above was. Actually, wait, I'll just go here.
How do you find the radius?
The radius is just the distance from the
That's that.
ends of points to the so you just use Pythagoras.
So even though this formula looks cooked, right? You don't even need to memorize this formula. You can just work it out based on your understanding of what a circle looks like, right? So your average of 2 numbers is just sigma x, sigma y divided by 2, right? Your radius, like you said, you're using Pythagoras, right? You're finding the horizontal part and the vertical part, and you're using Pythagoras, right?
Seems legit.
It's a bit harder to derive the transformed parts, but do you remember how I said we want to rotate this 30 degrees, right? Well, you have to plug it into these formulas, right? Let me show you this little pattern. Because this will look different depending on the different topics, right? And this one's -2. Okay. Can someone tell me how to find this point here? Like say, like the y part, the y portion.
In terms of the red points.
Sorry, just the maximum shear stress, maximum tau. How do you find that in terms of a circle?
When you have to find the formula of the circle and differentiate it.
Nah, too much. Sorry?
Just like the radius.
Yeah, it's just the radius. The maximum shear stress is just the radius. So that's here. That's just the radius, right?
looks like it's
It's slightly different from this one. What is that? Yeah, so that's right. Yeah. Wait, is that right? Alright, anyway, I'll come back to that. I copied this down from the formula sheet, it should be right. Okay. Alright.
you want for it.
Before I take up too much more time, I'm gonna talk about how this relates, because the reason I bring up that the Morse circle is very important is because it's in week 1, 2, and 3. So you talk about it in terms of moments of inertia as well. Okay. Here's a question, for example, I've included. You have this shape, and it's asking for the principal moment of inertia and the moments of inertia, right? So I literally, oh wait, I don't know if that one-to-one corresponds to the question, but you can plot it on a Morse circle, right? Once you've figured out Ix, Iy, and your product as well, right? And those are the formulas there as well that I've included. You can do the same thing where you rotate your shape, say like 30 degrees, and you can graph it on a Morse circle based on this rotation, right? And those are the formulas there. Note that these look a little bit different. So here, in orange and in blue, I've highlighted for your moment of inertia, it's plus minus and minus plus, right? But if you looked at the stress one, that one's plus plus and minus minus. So they look a little bit different. As well as this one, that looks a little bit different from this one, which is minus.
And is that just something you have to remember, or is that on the
No, you have a data sheet. These ones are harder to memorize.
Okay.
What's U and V?
Oh, what?
Initial final.
Okay. So you have your XY plane, right? Your U and V planes is just your rotated plane, and they're all orthogonal. They're like 90 degrees from each other, pretty much. That's all you need to define a 2D plane. Wait, what was it? Perpendicular. Oh yeah, they're perpendicular from each other. Yeah, that's the other word for it. That's what your UV plane is. It's just your rotated plane. And usually 1, 2. 1, 2 refers to your max and min. So 1 being the bigger one, 2 being the smaller one. And lastly, I'll just quickly talk about this one. This is strain. Strain's a little bit weird because it follows the similar patterns in terms of sign to stress, right? But when you're plotting on a Morse circle, you have your shear strain divided by 2 on one axis. Okay. And the reason for that is this is a strain element. The strain element, right? It looks something like that. And as shear strain is being applied to it, it kind of like squeezes from 2 points. I don't know how else to put it, but yeah. Because of that, it's going to change a couple of our formulas. And by the way, yeah, how you would represent this is dy epsilon y.
So is it not squeezing from the ends? Is it just squeezing from the middle of the shape?
What do you mean, sir?
I mean, is that like y divided by 2 because it's like applied to the middle of the shape?
There's like a couple of ways you can draw. So for the stress element, right? So say we have this is a stress element. Rotating at 30 degrees, for example, you could draw it like this.
Yeah.
You can draw it like that, right? But you can also draw it maybe like, I don't know, this one's a bit messier, but you can draw it like this, right?
Yeah.
And so the same thing here, like, don't think of this element like you're rotating. Like, I think the way that they've drawn it here is just the most elegant way to represent Yeah, you know what I mean?
Wait, so is the purple square the original?
Yeah, it's the
And then
original shape.
Blue square is the rotation.
It's the shear strained shape. So it hasn't been rotated. We're just
Wait, so what was the point of the rotation explanation?
I haven't explained rotation for strain yet. So this is a different element. This is a strain element. This isn't a stress element right now.
Yeah, but you were trying to explain something.
Oh, right.
So
Kind of what I've drawn is, so here, this would be a stress element that's rotated, for example.
yeah.
It doesn't really. Actually, I think this is a bad explanation.
Okay.
I think what I'm just trying to tell you here is that this is just the most elegant way to represent the strain element.
Okay.
Yeah. Don't think of it like it's being squeezed from one corner and it moves or whatever. It's just this like the best way so it doesn't overlap with itself. Yeah. Sorry.
That's okay.
I'm just gonna cover the rest of the course, but not in detail, just because it would sort of, I think, defeat the purpose. So I guess the idea behind today hopefully would be Henry gives you an idea of like in a more detailed way what's happening in the first 2 weeks, 3 weeks. So that'll hopefully give you a head start, so that when you're looking at the lecture, the lectures you're not lost. So that was these first 3 topics. These 4 topics is what's going to be covered later on in the course. I'm not going to go into them into too much detail, but I'll just explain to you conceptually what each of those are, and then we'll wrap it up for today. Okay? All right. So, sorry, this was covered, and this. Okay. So the first thing to talk about here is axial deformation. So axial deformation builds on what Henry covered for stress and strain. So basically, really simply put, so this is axial deformation. If you have a rectangular cube, or a rod or whatever, right? And that's the cross-section area. Let's call this A. This is the force N, right? Axial deformation just looks at how to calculate what exactly that axial deformation is. So for example, E is NL over EA. All right, so if E is the deformation that's caused, the axial deformation that's caused, so this whole thing just kind of moves like that by E. N is the force that's applied, L is the original length of the element, E is the elastic modulus, that is what Henry covered before, and that's a material property, so every material has a different elastic modulus. Steel has a modulus of 200 gigapascals, concrete will have different elastic modulus, whatever it is, whatever material you're using, given the question. That's the elastic modulus here, and A is the cross-sectional area over which the force is applied on. It's really simple, right? So that's what axial deformations are. Now, the important thing to take note of is units. So Henry covered the unit combinations that work well in a given formula because they are the dimensionality is conserved. So for example, if you're sticking with SI units, then you stick with SI units. If you're using millimeters and newtons, so for example, the most common unit combination you can use here is millimeters for all lengths, newtons for all forces, and MPa for all stresses. All right, and if you maintain this, the formula will basically work. If you want to use SI units, that's fine. But in our course, this will probably be the most useful because your dimensions will usually be given in millimeters. You just have to be careful that if a question tells you that, the elastic modulus, this is a piece of steel, the elastic modulus for steel is 200 gigapascals, then we just need to make sure we convert that to megapascals before we chuck into the formula, and then everything will make sense, right? So if you're expecting a length dimension to come out, then that length will be in millimeters if you stick to this, right? Okay, so that's the easy part of it. Where it gets slightly more complicated is if this thing has a weird shape, right? So for example, if you look at this formula, right, we have n. N is consistent over every cross section of this element, right? So I'm applying the force here at the end, but this force is also experienced here, all the way through. The force stays the same throughout the entire element longitudinally. That's the first thing. The next thing is the length. The original length obviously doesn't change with shape. The original length stays the same. Elastic modulus stays the same, right? It's one material, it's not two. And the cross-section area also stays the same. That's why we can use it as a simple formula like this. But if any of these things change, like for example, if your area is changing, which means you've got a shape. So for example, something like this. Something like that, right? And you're pulling this. Now, that's different because the area, the cross-section area changes across the length of the element. Okay, so for example, in a question like this, let's say the force here is N, that's the area at the end. And let me just give you an axis here. Let's call this Y and let's call this X. Okay? Not the same Y and X that Henry was talking about. I'm just giving you an axis. Okay? So let's have a look at this. Now let's say the question is asking you for this, calculate what the elastic deformation is. This formula still holds, but we just have to look at it a bit differently because now, let's see what's changing across the length. N. Does N stays the same across this entire length? Yes? No?
I think it's no.
Okay, so does N increase or decrease?
It will it doesn't increase or decrease, but it spreads out more across the shape, I would guess.
Right. So you're talking about stress or force?
So not force, yeah. So force will stay the same.
Right, so the total force, right? Yeah, if I'm applying 100 kilonewtons here, there's 100 kilonewtons here as well, right? So, the force stays the same. The stress changes because the area changes, right? Is there more stress here than here? Is there more stress at this end? Yeah. Why? Yeah, because the area is tinier, right? But the same force is going through. Okay, so N stays the same throughout. What about length? Does length stay the same?
But the original length.
Yeah. Does the original length change at all? Like as you move from left to right?
Yeah.
It's kind of a question that doesn't really make sense, right? But I mean, the length is the length. So the original length. So this is a constant number. Okay. Elastic modulus, is it the same? This one material.
Same material.
It's the same, right? So if this whole thing is one material, elastic modulus is the same. Area changes. Okay, so you have a look at the formula and you highlight, all right, in this thing, this is changing. Okay, now how is it changing? Is it changing in a discrete manner or is it changing continuously? Continuously, right? So if it was changing discretely, that would be something like this. Right? Here the area is changing discretely, here the area is changing continuously. Now, pause this first. I just want to talk about this. In this situation, when the area is changing discretely, what can we do? We can say that, all right, I can still use this formula, it's just that this formula will hold at discrete steps. Right? So for example, this is shape 1, this is shape 2, this is shape 3. Right? I can say, all right, there's some force N here that's pulling this entire thing apart. I can say, all right, the total elastic deformation will be NL1, so this is, let's say this is L1, over EA1, plus NL2 over EA2, plus NL3 over EA3. Make sense? The formula holds at discrete steps, okay? So when it changes discretely, it's still pretty simple, right? It becomes more of a problem when now we're looking at this, right? Because it's continuously changing. So let's just break this formula up now so that we are still trying to find E, okay? What is constant? N, L, and elastic modulus is constant, so I can write that down here. but area is changing. Okay, area is changing with respect to x. So let me just write area here, but because it's changing with respect to x, you'd have to do that. Okay? So you take all the constants out, and the thing that's changing, you find out what it's changing with respect to, and you write that down first. Okay? Now our next job is area changes with respect to x in a certain relationship, right? Like say when x is equal to 0, this thing is, area is pretty huge. When x is equal to whatever that number is, but according to the length, that area is smaller. So now our job is to figure out what that equation looks like based on the geometry, right? And that's just purely a geometry thing. It just depends on what the shape is. But yeah, so let's say in this case, just draw it a bit more. So like let's say this is y, and let's say this is some number 10. This is some number 5. I'm sure you will be able to work out a relationship between the cross-section area here. So let's say this width stays the same, right? And this width stays the same. You should be able to figure out a formula for area as x goes from 0 to, let's give this a number. Let's say this is 20. Okay? And that formula for area will be in terms of x. Yeah? Everyone following so far? Right? So this will be an this is basically a formula with just a bunch of x's inside. And it's a formula that calculates the area as it changes from x equals to 0 to x equals to 20. And your upper and lower limits will be 0 and 20. And then this is just a math question, and you get your answer. Okay? Now, in a nutshell, that's really what it is. The only thing that changes with respect to the question is what exactly that shape is. So this thing here changes depending on what the shape is, right? You won't be getting any cooked shapes or anything. It's just going to be like something basic that you can solve, right? The point of the topic is not for you to. It's not to test you on how to define a shape mathematically, because it's not a math topic. Like it's not a math like subject. It's just for you to recognize that this is changing with respect to x. These don't change, therefore that's how you calculate elastic modulus. Make sense? Okay. The last part of this is, let's go back to discrete, right? So this makes sense when I'm pulling it this way, right? Now, what if, I'll give you a question now that looks like this. Okay?
Except soft logo.
No, it's a week 5 question 2.
Yeah.
No. Actually, it is.
Actually, it probably is.
It probably is.
That's,
She's done this for years.
so where's n for the question?
Sorry?
So where's n? Where's the force?
Okay, let me give you some numbers, right? So this is 10, 20. Let's say the 20 is applied across, sorry, it's not two 20s. Let me just, let's just put it here.
Oh, I think I got it.
Okay, now the question is asking you how much is this thing going to get squished? So, can you guys see?
Wouldn't you just repeat the formula, but then when you go to the second shape, you do the 20 and the 10?
Correct. So, okay, so this is 1, this is 2, this is 3, right? So E is equal to, what's the n here?
10.
For shape 1 is 10, right? So 10 L over EA, let's call this L1. And then for this one,
30.
why is it 30 here?
Because the force from 10 goes all the way through, but then add in the 20 for the second shape.
Exactly. So it's 30 here times L2 over EA, and then the last one is 60 times L3 over EA. You can still do it discretely, right? Because the formula holds, everything is constant at discrete steps, right? You can see how it doesn't make sense here because you can't do discrete here, okay? If it ever gets confusing, how much force is going through a particular point, very simple, all you gotta do is just take a cut at any point here, and then you can draw that out, right? And then ask yourself, all right, so there's 10 there, how much axial force is going through here. It has to balance out. So it's 10. If you take a cut here and you just focus on everything above, how much axial force is moving through the shape? It's 30 because there's only 10 and 20 on the side. And then you can take a cut here and then it'll be 10, 20, and 30. Okay? That's free body diagrams. Okay, so that is axial deformation in a nutshell. Questions on this? No? Alright, so those are the basic principles. So those are the basic principles of axial deformation.
Should I take a photo of
Yeah.
you, Robert? Yes.
Cool. Alright. Now let's talk about bending. Okay. When it comes to bending, that's what Henry was talking about, which is the engineer's flexural theory. There's two types of bending that you'll look at in this course, or three actually. One is elastic bending, one is inelastic, and one is composite. Okay? So I'm just going to touch on each of these conceptually. So elastic bending refers to the bending of an element that is completely elastic. Okay. Right. So for example, let's say you have a beam here which is supported on two sides. Okay, you've got a pin on one side, you've got a roller on the other, and let me just give it some thickness. All right, and let me put a load on here. Okay, now let's say this load is 40 kilonewtons. Can you guys tell me what the reaction forces are?
20.
20? Yeah. Of course, just assuming, let's say this is 3 meters, this is 3 meters. Okay. So the reaction force here is 20, here is 20. Any horizontal reaction forces here?
No.
No. Okay. Because you only have vertical forces. All right. So these are the reaction forces. Okay. Now, this is just a recap of 1300, by the way. So what does the shear force diagram look like? Over here, what happens? Up or down?
Oh yeah, up then down and then this way.
So up by how much?
20.
20.
Yeah, then
And then between here and here, no change. And then what happens here? So negative 20, and then no change, and then 0. Alright, now let's look at the bending moment diagram. Now before I do this, can I ask you guys, how many of you are doing civil engineering? Sick. Alright. Sorry, who's not doing civil engineering? I guess all doing civil engineering. Oh, so.
Yeah.
Okay, brilliant. Okay. Now the reason why I bring this up is because there is a sign convention for bending moment diagrams that is only relevant for civil engineering, but for every other engineering, it's the other way around. Yeah. Okay. What I mean by that is, when it comes to civil, or more specifically structural engineering, right? Positive is below and negative is on top, for a very good reason. Okay. But for every other type of engineering, it may not really be relevant. Okay, because the type of analysis you do would be different. So in structural engineering, the reason why positive is written on the bottom and negative is on the top is because you want the bending moment diagram to be drawn on the tension side. Okay. So what will the bending moment diagram look like for this triangle?
And until it gets
Above or below?
or below if it's positive.
Right. Okay. And then you can work out whatever this is. What is it?
Yeah, 20 times 3.
60. Right. Okay. Alright, that's the bending moment diagram. Now, why is it drawn like this? It's because when you bend this physically, how will this deform? It'll kind of move like that. Right? That'll happen. Now, when this happens, think about what's happening on the top fiber here. Right? You're taking something and you're bending it. The top fibers here will compress together, right? So the top fiber here will kind of squeeze together. Now the bottom fiber will be in tension. So the bottom fiber will pull apart. So that's why if you draw a bending moment diagram in structural engineering and it's drawn on this side, it basically means every point on the bottom fiber from here to here is in tension because it's on the bottom, right? If the bending moment diagram did something like this, right? That strictly means that from this point to this point on the beam, every bit of top fiber is in tension, and from this point to this point on the beam, every bit on the bottom fiber is in tension. That's literally what the bending moment diagram is supposed to show you, right? So in reality, once you start, if you guys do structural engineering and you go out to design, you'll see bending moment diagrams without any signs at all, because the signs aren't as important as shape. Like the side you draw it on is more important. Okay, so you'll never see like I'll design this for like negative 50 kilonewton meters because it's like, well, this is negative mean. But if you see the bending moment diagram, you'll be like, all right, so it's tension is on this side, right? Etc. So that's why that's important. All right, so tension is on the bottom and compression is on the top when you bend it like this. So if I were to look at the cross section, let's say this is just a rectangular cross section like that. Okay. If I were to draw out the cross section here at this point, it'll look like that. Yeah? Now, we've already determined that compression's on the top, tension's on the bottom, right? If I draw this out, this stress diagram out, that stress, let's say this is the compression side and this is the tension side, it might look something like this. Right? Now, the way to actually visualize it is this is the cross section, right? So if this is sticking out of the board, that's the beam. It's going to be weird, but you try. Imagine this drawn this way on top of it. Okay? So your compression is sticking out and then your tension is like into the board, for example, right? That just means that this entire part is in compression and this entire part is in tension, right? Increasingly so. Which means there's zero stress here, and as you move away from the neutral axis, so this thing here, which is where your centroid is, that's why it's important to understand how to calculate centroids. That centroid is called the neutral axis. And as you move away from the neutral axis in the compression side, it becomes, the compression increases more and more. As you move from here downwards, the tension becomes more and more. Make sense? Right? So that is, being able to draw this correctly is a big part of elastic bending. Okay, and of course there'll be formulas that you'll learn, like sigma is equal to negative my on I, basically to calculate what this sigma is at different points along this cross section. Don't stress about this now. I'm not going to touch this now, but that's basically what it's doing, right? So for a given, if you apply a given moment here, right? Like in this case, it's 60 kilonewton meters, and I'm interested in the middle cross section, which is experiencing the most moment. If I chuck in 60 in here, right? Y is just basically how far I am away from the neutral axis, and I is the second moment of area, which Henry already covered. How to calculate for the entire shape. You will be able to calculate what stress is, right? So the higher up you are, the larger the Y is, the more the stress. Okay, and then if you hit in the opposite direction, this becomes negative, and then you get stress on the other side. Okay? But that's basically what it is. That's elastic bending. Inelastic bending, which is the second part of it, is, okay, let's say that my material is not perfectly elastic. So as Henry was covering just now, if your steel material is like that, you're in the elastic region, it means that you've stressed it, and if you release the stress, it goes back to what it was before. But if you stress it high enough, it becomes plastic. Yeah, exactly. So you'll start to see that, right? And so if you release it when it's plastic, it goes back like this, and it'll leave a permanent deformation there, right? So why this is important is because what happens when something becomes inelastic, all right? So let's imagine this again. I've stressed it at 60 kilonewton meters. Let's say 60 kilonewton meters is the limit. Okay? Let's say at 60 kilonewton meters, it's like about to start to yield. So that's the yielding point, right? Once it yields, it becomes so squishy and like you permanently mess it up. right? So when it starts to yield, what happens is this starts to happen on both sides, right? What this is the yield stress. And the principle behind it is a material cannot take any more stress than the yield stress. Once the yield stress is reached, it basically can't take any more stress. Okay? So sometimes you would see it kind of in theory, in simplified beam theory or simplified model of steel, you might see something like that. Right? That's the model that we'll be using. So for example, basically all it's saying is once you've reached a particular stress, for steel it's probably around 500 MPa, okay? It can't take any more stress. So it'll start to plateau out like this. Okay, which means what areas have you messed up now? You've messed up this area. Like it's gone, like it's never gonna go back to being elastic anymore. You've messed up this area. Completely plastic. But this part here is still elastic. Right? If I bend it a bit more, then this will rise. Until you get to a point where it's fully plastic, you've permanent, like the whole cross section is damaged, it'll look like this. Okay? Where complete plasticity on the top, complete on the bottom as well. And doing the same calculations that we've done on elastic, you can do on inelastic as well. You just got to know that there's a different set of rules that apply. Obviously, this formula doesn't apply. Why? Because this is not completely linear anymore. It's bilinear, right? It's not a triangle anymore. So this formula won't apply. You'll use a different set of formulas, which is what the lectures will cover. So that is inelastic bending. And then finally, we have composite bending. Composite bending, Mike, could you raise this? Yeah.
Or for me to go further, yeah. There's not a question.
Okay. Composite bending is where you've got two different materials that are bending together. Okay, so for example, if you have a T section like this, but then I tell you now that this thing is made of steel and that thing is made of timber. By the way, which is stronger, steel or timber?
Steel.
Steel, okay. So which can take more stress, steel or timber?
Steel.
No, isn't that one has a lower elastic yield?
Yes, but let's forget about the plastic limit for now.
Wait, doesn't it depend on the area then? The stress. Well, are you talking about generally?
No, in general, yeah, in general. Which can take a larger stress? If you compare between steel and timber.
It would be steel generally.
Okay, actually, let me refine that. So let's say you've got a particular shape. The shape is the same. Two identical pieces. One is timber, one is steel. You basically apply the same force on both, right? So 500 kilonewtons on steel, 500 kilonewtons on timber. Which one is experiencing more stress?
Neither. Right?
Very good, because their areas are the same. The shape is the same, right? F over A.
Yeah.
Okay, but
Which is gonna be a trigger.
no, you're right. That's exactly it. But in a case like this, if it was all the same material, right? If it was all the same material, what would happen? You would, and it's in elastic bending. If I were to draw the stress distribution, it would look like that, right? If it was all the same material.
Yeah.
But because these two are composite with each other, which means the steel isn't working independently from the timber. They're both bending together, right? In that case, what will happen is the one with the higher elastic modulus is the one that takes the larger stress, right? So which has a larger elastic modulus, steel or timber?
Timber has the larger one. Oh.
Elastic modulus. Steel is the stronger one, right? Think about it. The one that has the lower elastic modulus is the one that bends more for the same load. So if I take a piece of timber and I bend it, like it'll bend a lot. Sorry?
The one that will break.
So elastic modulus is stiffness, right? So how much it's gonna form based on the stress that you apply to those atoms. So it feels stiffer. That's the highest slope, right? On the graph.
Yeah, so for example, if I were to draw it out like that, stress and strain, that would be steel. This is timber. Right? It's like it's significantly, like it's an order of magnitude stiffer than steel. Sorry, stiffer than timber. So in this case, when composite bending happens, when it comes to timber, right? Let's say the stress is like here, right? But at some point at the interface between timber and steel, the stress will jump. Okay? For the same strain. Park that thought, I'll get back to that. So the stress diagram looks like this. Okay? Let's say that you can use the centroid formulas to calculate the centroid, but of course, because there are different areas, there's another method to calculate the centroid, which I won't touch. Again, you'll be having the lectures, but you'll be given a formula to calculate the centroid of a composite shape. Let's say the centroid somewhere here. All right? That's what your bending stress will look like. Now, this is the stress. The one rule that you should know is, what about strain? Right? So what's the difference between stress and strain? Stress is the amount of force that's going through per unit area. Strain is the deformation, the physical deformation that's happening. When you're drawing the strain diagram, from physically, when you take this beam and you bend it, it's going to look like it's bending perfectly. Right? It's just going to bend. The stress each material is experiencing might be super messed up, but from the outside, the deformation is going to be consistent. So that is what the rule of plane sections remain plane is. Plane sections remain plane. Okay. Basically what this means is this strain diagram is always linear. You're never going to see a curve. You're never going to see it jump up and down, whatever. A strain diagram is always going to be from the top to the bottom, one line. Okay? What this means at this point here in the stress diagram is when you're talking about timber, for a given strain point, timber has less stress. Right? But when it comes to steel, for this same strain point, steel experiences a higher stress, which makes sense because steel is the stiffer material, right? If they're both deforming the same, steel must be experiencing a much higher stress than timber, right? If you want to put them together and stretch them and make sure they strain the same, if they deform the same, then obviously one has to experience a lot more stress than the other for them to both deform the same way. Yeah, makes sense? So if you take a piece of timber and you put a piece of steel underneath and you stretch them, obviously they're not going to stretch the same, right? But if you want to find a way to force this thing to stretch the same way, it means that you must be applying a much higher force on the steel, right? Because steel takes heaps of force to stretch, but timber might not take as much force for it to stretch the same way. That's exactly what this means, right? For the same strain, timber stresses much less than steel. And that's basically composite. Any questions on this?
Not on this, but how would the strain diagram look for an inelastic bend?
It will still look like this.
Is that the same?
Yeah. Yeah, because just because something has yielded doesn't mean it still can't continue to deform. Like an object can continue to deform even though it doesn't accumulate any more stress. It just means it's yielded. Yeah, it's deformed. So like, see here, like over here, as you're going up this elastic ladder, yes, you need more stress to get more strain, but once you reach this point, you can keep straining it and it won't accumulate any more stress, right? Basically, it's like a rubber band, and once you stretch it enough and it goes plastic, it becomes so easy to just pull, and you've just messed it up. Or like Play-Doh or something. Right. Can I erase this? Yeah. Okay. All right, let's talk about deflections. Okay, this is just a way for you to calculate how much something deflects under a given load, right? So for example, again, let's say we have this beam. It's a piece of steel, and I've got a force here, say 20 kilonewtons. It's in the middle of, say, 5 meters, or it's 10 meters long. I want to jump straight to the bending moment diagram. Can anyone tell me what it's going to look like? Yes, it's the same as what we had before, right? Triangle at the bottom. What is the maximum moment? Sure?
Is that 2?
Yeah.
Sorry. This is 20 kilonewtons. Sorry, so that's 10. That's 10. What's the moment here? No, this is not the shear force, this is the bending moment diagram. 50?
Yeah, 50. 10 times 5.
Yeah. All agree? Yeah? Okay. 50 kilonewton meters. Okay. So, again, I'm drawing it on using the civil convention. It'll be better if you guys are actually going to do civil engineering, it'll be better to get used to this, right? Because this is going to like mess you up if you learn it wrong the first way around, like you'll be struggling for like the next few years when you look at the bending moment diagram and there are no signs, that's even worse, right? So just remember it's always on the tension side. Okay, so that's the bending moment diagram. Now, what this topic covers is a formula to be able to calculate deflections. Okay, I'll write down the formula here for you. So EI dv squared, d squared v over dx squared equals to negative mx. Okay, what this basically is, v is deflections. Okay, because think about it, what will the deflected shape for this beam look like? The deflected shape will look like this, right? So this is basically, well, deflection is a function that you can represent in terms of x, right? At x equals to 0, v is equal to 0. At x equals to 10, v is equal to 0. At x equals to 5, v is v max. Yeah, so v is it's an equation in terms of x. If we, yes?
Is that negative mx, is that a function of x, or is that multiplied?
No, sorry, it's a function of x. Okay, so remember, v is a function of x. Moment is also a function of x. At x equals to 0, m is 0. X equals to 0, x equals to 10, m is 0. X equals to 5, m is 15. Right? M is a function that you can represent in terms of x. Right? But that function of m is 2 lines. Right? You've got your first line here and your second line here. This, most likely, you can represent in one equation. Right? V in terms of x, which is the equation of this curve. If you take this curve and you differentiate it twice, that's what this is. If you write out the equation for m, which is a function of x, that's what this is. And EI is just your material and geometric constants. Okay. The point of this is, I want to find out what my v of x is. I don't know what this is, because I want to calculate the deflections, right? So you start off from here. I know what this is, because that's this, right? I can write out an equation for m in terms of x, and you've learned that in 1300. Okay? So once I have this, then I can integrate this twice. So it's simple integration, it's not like super complicated. And you will get EI v of x equals to some stuff here with 2 constants, right? Because you've integrated twice, you'll get 2 constants. So our job now is to just remove these constants. How do we do that? We've got some information. At x equals to 0, v is equal to 0. Just because I know what the deflected shape is going to look like. At x equals 0, v is 0. At x equals to 10, v is 0. And these two will be enough to get rid of that. And now you'll have an equation for what V of x is. You can throw ER on the other side, it doesn't matter, right? And now you can find the deflection for wherever you want in your beam. In a nutshell, that's what deflection's topic
And
is.
deflection just means how much it goes down, right?
Or up, depending on the loading. Basically, once you've messed it up, what's it going to look like?
Yeah.
The final shape. Okay? Question on this? Oh, makes sense, yeah? The idea is just to convey to you conceptually what this is. Like, don't get bogged down in the formulas. When you get to the formulas, you'll figure it out. Okay? Right. We've got two more which we can talk about together. So,
sorry, let me just-
oh,
No, that's fine. That was like 2 lines.
okay. Alright, the last two topics are shear and torsion. They're not the same thing, obviously, but I'll just discuss them together. So, shear first. Okay. Now, what shear is, in a context of a beam, I really like discussing this with like civil engineering students because like if there are like other like students from other like aerospace engineering, they'd be like, wait, so in a spaceship, and I'm like, you've lost me. Because I'll spend the whole like term talking about buildings and stuff, and then I'll always be like, well, gravity is always 9.81, and then the aerospace dude is like, no, wait, it's not always 9.81, and I'm like, you've lost me. You've lost me. No, someone was like, why isn't it like why isn't it like 2? And I'm like, what do you mean? Okay, alright. Let's say we have a beam like that, okay? And there is a force here, okay? What happens, or let's say there's 2 forces like that, okay? That's pushing it apart. What happens is this cross section here, that's in the middle of these 2 forces, right? That's basically what a shearing action is. So when you in longitudinal, right? If you've got a beam and you hold it like that and you try and move it up and down, that movement is what shearing is. Okay, and when this shears, so we get this sort of action that's happening on the stress block, right? Just on the cross section, the way you would draw the shear would be, and this is where it's important again, and it comes up again. So I'll just reiterate what Henry had discussed earlier. The convention that we use for positive and negative shear, right? You can either just memorize what it looks like, or just picture an origin on your top right hand corner. Okay? If the arrows are moving in the negative direction from your top right hand corner, then that entire thing is negative shear. Okay? So for shear conventions, the sign convention is really, really important. Okay? And if with respect to your top right hand corner, if these are your arrows, then that's positive shear. You'll never find it where that's happening. Okay? Because that's not an equilibrium. This will never happen. Right? So that's how you get, that's how you know what your stress block looks like. Now, the interesting thing here about shear is shear doesn't obviously move or doesn't flow through your system, through your cross section in a uniform manner. Okay, it won't, because it depends on the shape. So if I draw out some of the stress distributions for shear, it'll look something like this. So if I'm just drawing out a shear stress, which is tau, by the way, that's how we denote shear stress. If I draw out a graph of how this cross section experiences shear stress, it looks like this. Okay, which means at the tips it's not experiencing that much shear stress, and in the middle it's experiencing the most. So in symmetric shapes at the neutral axis, that's where you get maximum shear. Okay, and that's why in like buildings and stuff, if you have like a steel element that's undergoing a lot of shear, the propagation of failure tends to happen from the middle, if it's shear failure. Okay, different for concrete because in real life you've got reinforced concrete, so you've got steel that's going through the concrete. It might not necessarily be symmetrical, but in a perfectly symmetrical object, if you try and shear it, the shear damage will propagate from the middle because that's where the largest shear is. Okay, and of course for different shapes it'll be different. So for example, if you have an I-beam and you're applying shear to it, the graph will look something like this. It'll be, because there's less area here on the top, it'll be less shear, and then it'll basically peak out like that, and then comes back here at the ends. Okay, so for an I-beam, right, when it comes to shear, what is doing most of the work? These two horizontal things here or the vertical thing here? What is doing most of the resistance to shear?
The one. The middle one.
The one in the middle, exactly. It's experiencing the most shear. See? Right? This is shear stress. Okay? That's why an I-beam is really, really optimized, right? Because when it comes to bending, so by the way, in an I-beam, these things are called flanges, and these things are called webs. Okay? So what does most of the work in bending, a flange or a web?
For bending.
For bending.
Flange.
Flange, right? So if you imagine the bending stress diagram I drew out for you earlier, the maximum stresses are at the ends, right? So in bending, the flanges do most of the work. But why is a web really important? Because if you in shear, that's the shear stress diagram. So the web does most of the work for the shear. That's why it's really optimized. Because each thing is sort of doing its own job and it's not really experiencing, not in a large way anyway, it's not experiencing both, the worst effects of both. Okay?
It might be helpful to draw up the tau formula with the B or not as well. The width.
Yeah. So I'll draw this out here for you. So now the point of this chapter is basically to calculate on this graph what any of these points are. Okay, so the question is asking you what is the shear stress at this height, or this height, or this height. You should be able to get that. And the formula for that is VQ over IB. Again, I don't want to go into it too much in detail, but basically what it is V is the entire shear force that's being applied on the entire cross section. I is the second moment of area. So again, you see it keeps coming up again. That's why it's really important to get good at calculating second moment of area, because it's going to haunt you for the rest of the course. And if you become a structural engineer, you're life, right? So B is the width of the section you're taking a cut at, and Q is your first moment of area, which is what we sort of talked about earlier. Okay, AY, and that's also called shear flux. So I'm not going to touch on this, okay? Just because then, like, you'll probably forget it. Yeah. But again, conceptually, my point is to just convey this to you conceptually. Okay? And of course, these shapes change for different cross-section shapes. Like that's what it is for an I-beam, that's what it is for a rectangle. And for different classic shapes in structural engineering, there are set graphs of what this look like. It'll be on the lecture slides. It's good to familiarize yourself with them just so when you're doing a question, you just know sort of what it's supposed to look like. Okay? And the last thing I want to talk about is torsion. So torsion is basically the exact same idea. We just want to know what the stress is going to look like depending on how you stress it. So we looked at bending, we looked at shear. Now it's looking at what happens when you twist something. So for example, if you've got a circular rod, like that, and you twist it, what does the stress distribution look like? So if I draw the cross section here, right, for a circular rod, and I'm twisting it like this, the stress distribution will look like this, right? It's going to be largest at the point you're twisting it, and in the center of rotation is going to be 0, right? So you just imagine like a piece of jelly and you're turning it around, you'll kind of see how all the, anyway. Yeah. Get the idea? It's just because at the point of where the force is applied, that's where you get the maximum torsion. Okay. There is another formula here for torsion. The main formula. I'll write it down again. I won't go through it in too much detail, but basically it's a way to calculate what the shear. Again, it's a shear force, by the way. It's just a torsional shear force compared to this shear, which is normal shear. Okay. So just get used to those terms again. That is normal shear because it's a shear force caused by forces that are normal to the longitudinal axis of the member. This is a torsional shear force from twisting. Okay, and this formula here, again, I'm not going to go through that, but basically this formula is what you can use to calculate the shear stress at any point from the center of your shape throughout till the end. And of course, this is stress. So we need a physical deformation version of that, right? For bending stress, what was the physical deformation for that? Strain, right? Normal strain, which was, so I can write this down here. For normal stress, the deformation version of that was strain. For normal shear, right? What was the physical deformation for that? Shear strain, which was gamma, right? Now for torsion, which is also tau, but I'm just going to write here tau torsion. The physical deformation of this is, so for example, in strain, right, you'll have, you can have it in millimeters as well, right? Over here, you can also have it in millimeters. For this, it's also gamma torsion, but the physical manifestation of that is twist, which is an angle, right? Because if you take a certain element and you twist it enough, then you can be like, oh, I twisted it like 5 degrees, right? With respect to the center of rotation. So the question here would be like, I'm applying this amount of torque on this thing. How many degrees does this twist by, right? So there is a formula for twist, which is, again, I won't discuss this here. But basically, if you have the torque that you're applying, the given length of the element, J is a torsional constant, which is dependent on the geometric shape, and G is your shear modulus, which was in Henry's notes earlier. You can calculate the angle of the twist. Okay. In a nutshell, this is the course. So if you have a look back to everything we've discussed today, what you're going to find is essentially what this course is about is applying forces on different things in different ways and calculating what's the stress and what's the strain, right? What's the physical deformation? If it becomes plastic, what is the plastic deformation? That's literally all it is, right? Even through deflections, that's what you're looking at. Even in bending, that's what you're looking at. So the point of this course is it's teaching you how to analyze a structure, okay? And because we're all doing civil here, it's basically for structural elements like beams, columns, etc. for buildings. Okay, so this course is really good because it teaches you how to analyze for a given loading situation, what are the stresses that are going through this element? What's the normal stress, what's the shear stress, and all that kind of stuff. Later on, after this course, in 3rd year and 4th year, when you start learning timber, steel, concrete, and all that, that is the other side of the story, which is, okay, now that you've already learned how to analyze a structure, you know, okay, there's 50 MPa of normal stress, this is how much is straining, etc. Then the question is, can this concrete beam withstand that stress or withstand those forces? So that's the other side of the coin. That's the design side. Okay. So this is, I think, one of the last few courses you're ever going to do on analysis. It goes into it fairly in depth, and that's why it's an ENG course, because it's useful in almost all engineering disciplines. But once those in civil, once you start doing steel, timber, and concrete, then you're basically going to be checking whether for these stresses the timber will fail, will the concrete fail, will the steel fail. That's the other side of that story. So you'll never touch on analysis pretty much after this course. Have you guys done structural analysis yet? No? All right. So that 2303, to be fair, doesn't touch on stresses and strains. This is literally the last course that touches on stresses and strains. Okay. That one other analysis course that you'll be doing is basically get funky with moment diagrams and shear diagrams and just basically get it in a complicated structure. If you were to draw a building, what does the bending moment diagram look like for the entire frame? Yeah, but it doesn't touch on stresses and strains. One more thing just to mention is for you to appreciate, I guess, the importance of understanding it well at this stage. Because if any of you want to do structural engineering, like later on when you start working, I promise you, you'll literally be doing these same things. Right? This is like drawing out a stress diagram or a strain diagram is a big part of structural engineering. Even once I graduated and I started working, I'd like pull out my uni notes and hope I didn't forget what I was taught. Okay, so since you're about to start learning the course, it's good to, if you're interested in that field, this is like your bread and butter. It's like your fundamentals. Okay. Any questions? Cool. Right. No.
Can I get a round of applause for that?
Henry.
Yeah, I'm just gonna do this last bit of the recording. So this is for the review questions. All right, this is our one player. This is Caden. Thank you, Caden. We're gonna judge every answer you do. So basically, yeah. So this is from Efficient Engineer, the YouTube channel.
The what?
Efficient Engineer.
Yeah.
I don't know if you watched any of those videos for maths or whatever.
Yeah.
Anyway, it's like a YouTube channel. And they have this, the first example, which is a thought experiment. It's like you have this bridge that's crossing this little canal. And yeah, like if you were to step on the one on the left versus the one on the right, which one would bend more, right? And it's the one on the right that's going to bend more. Yeah, the one on the left is going to be stiffer in that direction, right? Yeah.
So the correct answer is the middle.
Yeah. And when I say stiff, right? So E multiplied by I, that's called, those are two terms grouped together, and that's called flexural rigidity. The E component is your elastic modulus, right? That's material stiffness. I is your bending, right? Your bending resistance. So that's like shape stiffness, basically. So this is to do with shape stiffness, because it's the same material, right?
Yeah.
So it's about the orientation. This door tilted me so much that I took a photo of it and then decided to turn it into a question, right? So
Stupid fucking.
okay.
I was looking at the image. I was like, that's not that bad. Then I saw the question.
Yeah. So basically, you pull on this door in the mech building, right? And okay, I see where they're coming from, because like it's easier to hold in that direction, I guess. But it's so much thinner in this axis that it literally bends. Like when you pull on this metal door, it like it like deforms so much, right? Yeah, and it's funny because it's the mech building basically, and they should know about this stuff. But anyway, yeah, but it's due to low moment of inertia. You said product of inertia, but it's true that the product of inertia is 0 because it's symmetrical or whatever. But that's not the reason. I didn't really cover like the usefulness of product of inertia. I think it's to do with torsional effects. So with your moments, right, you have two types, and it depends on your perspective. You have your bending moment, which is what we're talking about here, right? So like for a beam, bending moment's like over the entire beam.
Yeah.
And your torsional moment, which is what we're talking about, what Prash was talking about in the last topic there, you're twisting. Product of inertia is to do with twisting.
Yeah.
Okay. It pertains to that.
I probably should have picked that answer because we didn't even mention product of inertia.
Yeah, it's the thing which I said, the balance of the shapes and stuff. I kind of only talked about it mathematically. I didn't really talk about it.
Is that product of inertia?
I X Y, yeah. And on your I more circle, it's your up and down axis.
Yeah.
That's your product of inertia.
Dude, it's like going back through the unit circle.
I never
Yep.
remember shit about it. So.
And then
I had no clue what I was doing in this one.
oh no, it's basically a hollow section, right?
Yeah.
So to get your area of moment of inertia, I'm just trying to demonstrate here that you can subtract off
The big one.
components as well. So it's your shape, and it's your big shape minus your small shape. That's pretty much it. I just did a bit of tricks here because I said that big B is equal to big D.
So what? Oh, it's the power of 4 because we've only done the stuff to the power of 4.
It's only to the power of 4
Because it's the shape.
because it's a square. So a rectangle has a different width and different depth, right?
Yeah.
Wait, so when we were doing the questions, b to the power of 3.
Yeah.
That was for a rectangle and was
yeah,
it the same thing?
let me get a mark. Yeah, basically, what's this, right? So I'd x for a rectangle, something like that, was b d cubed on 12,
Yeah.
right?
Yeah.
And if this is for a square, what do we know about square?
All the sides the same.
All the sides are the same, right? So b is equal to d.
Yeah.
So
Oh,
it's just
I got you.
yeah, b
I
to
got
the
you,
power
I got you,
of
I got
4.
you.
That's where you get your millimeters
Yeah.
to the power of 4 from.
I
Is
get
it
you.
y with a cube?
That's
Why is it cube for rectangle?
It was just
It
is.
just is, bro. No, dude, I remember.
It just is. Or
No, okay. Little short story, right? So when I was working at CBB. Oh, did I?
I don't know, maybe.
Oh, okay. Well, I'll tell the other guys, right? So when I was working at CBB, I was working under a grad engineer. He's just like maybe like 1 or 2 years older than me, and a project engineer. He's quite experienced, right? And then the grad engineer, I kept asking questions, but he didn't know the answer to it. But he would say, "It's the way it is because it's the way it is."
Yeah.
Right?
So is it?
And then I was like, "Oh, okay." And then the project engineer was like, he explained stuff properly, and I was like, "Hey, like." The other guy, I asked him this, and he's like, "Yeah, it's just like the way it is." And the project engineer's like, "If anyone ever tells you that, it's because they don't fucking know." It's right, and they just don't feel bothered to like answer you, right? So yeah. Anyway, if you hear that,
So is this
it's the way it is because the way it is. They're just failing to admit that they don't know the answer.
Is it? So is this just because it is?
What was the question again? I lost my mind.
Why is it cube for a rectangle?
Why is it cubed for a
Okay,
rectangle?
I'm guessing it's to do with the ratio.
Yeah, it's something to do with ratio. I'll show you in contrast the IY one, right? It just takes a bigger component of.
I'm gonna fuck that up in an exam. I'm gonna like not move the cube.
Dude, the problem with geometric properties and like this, these formulas and shit, is you plug in one number wrong, the whole thing's wrong. It's super tilting. So it's all about attention to detail.
Does this have carryover like this course?
Oh yeah, so Moodle, right? They take your answer from the box,
Yeah.
and then like they can account for carry-on error pretty easily. Because it's like if your answer from this box was wrong, but then your next step was right according to that, I think yeah, you're allowed to have some carry-on error. But if your final exam, I think it's like handwritten, right? I don't know, depends on the marker. But I'll be honest.
Putting zero
my-
in every box and getting carry forward.
The first 3 weeks that I covered, the first 3 weeks that I covered are the really boring like a fucking Excel spreadsheet could do it kind of topics, right?
But they're all counts, right?
Yeah, they're all like pure maths pretty much.
Yeah.
Prash's topics is where it gets interesting and where like the understanding of like engineering and like physics has to come in. Yeah. Anyway, sorry, I've yapped on. But yeah. So but you answered this before, Keaton. The product of inertia. That's the IXY. It's negative skewed because of it being in the top left and bottom right.
We did this
right?
one together. On the board. I wasn't reading the question.
Yeah, but just remember it's to do with twisting, right? So that's why it has like if it has like this shape rather than a symmetrical shape, then it's gonna have a non-zero product of inertia. Oh, here we go. So this is just to do with how to read one of these diagrams. So your sigma x is going to be positive 2, right? Your sigma y is going to be negative 1 because it's pointing in, like compression, right? We're not working with soil mechanics conventions, we're working with soil mechanics.
So pointing outwards is positive and pointing inwards is negative.
Yeah.
And the shear would be negative because it's towards the top left
Yeah.
and bottom right.
Yeah, those are the origin points that Prash is talking about, as in like it's away from the origins, which.
Yeah, but the 0.5 is going to be negative, yeah.
So it can't ever be on a diagram where like the arrow goes like.
Yeah, so that's what Prash is saying. So if you have like a counterclockwise one, for example, it's not in equilibrium anymore. So it's moving, and we're talking about dynamics, which isn't true. Like this course is 100% statics.
Okay.
There's no dynamics. Fluids is like 50% dynamics still.
Okay.
Yeah. So everything is Newton's first law. F equals 0, right? Sum of forces is 0.
Easier.
It's like, you know what I mean? It's easier but harder. For some people, they found it, like I found this course easier than fluids. Some people like fluids more.
Like,
Fluids is more applied, to be honest. This is like super theoretical.
Fluid is all that.
Half. There's a little bit of statics. Just my. So when a body of water is still, right? It's when a body of water is still, like we can have these kind of like sluice gates, right? You have these like floodgates, and then you can have like a pinned
Okay, I
or
got
something.
you.
Yeah, and then it's about like the moment acting on this gate due to the hydrostatic pressure, right? Yeah. Anyway, yeah, like you literally hear the word static in the topic if it's about statics for fluids, right? It's like hydrostatic pressure or like hydrostatics, full stop. Yeah, that's all to do with statics. IUV, product of inertia. Yeah, that's negative. So wait, did you know why you got this one right?
I guess.
Oh, okay. Basically, you rotate it, right? I'm gonna draw the rotated. So that's the UV plane, right? That area there is gonna be your positive area, right? But this leftover one's gonna be negative.
Oh.
So the negative part's way bigger, right?
This is making more. That's kind of cool though.
Yeah. Like that's why I talk about it in terms of like I called it the balance of area, right? Yeah, it's about like this balance in the quadrants.
Guys, remember we haven't even started.
Yeah, you guys are well and truly ahead of everyone. It's fine. You'll be fine. Yeah. So this is just plugging in more circle numbers. You got this one right, which is good. But like, yeah, it's just so both these values that were given are the values in the center.
Oh,
So,
okay.
Yeah, and tau xy. So it'd basically be one point here and the other point's here. So your Morse circle xy line is like straight, bang up and down, right? And then it's saying what are these? How do you find these points? And it's just
Half the time for this question was me literally just reading the options.
and seeing the vibes. But yeah, do you understand now after the explanation? It's just circle geometry, right? Yeah. And then I said what can be said about this. So there's a few tricks here.
It's really funny because I like x'd out radius of the circle is equal to 50 and I x'd out the correct answer because it was basically the same thing. It was saying kind of the same thing.
Okay, well, how would you find the radius of the circle?
You would take x and y and then divide by 2.
So then you would find the mean, right?
Yeah, but that's not. But it's
And then you just take that
the
middle.
radius isn't 50, right? But isn't the principal stresses like the radius?
Well, radius. Okay, well, the radius. This is diameter of the circle, right?
Oh my god,
Radius
it
is like the
is
distance.
right! Oh my god, I just got it! I just understood what the question was
Yeah, no, that's
asking.
right. No, but the radius, what would it be?
The radius
The
is
diameter is 75, right?
Yep.
So what's the radius?
like 37?
Yeah, 75, right. So radius is actually that. You can spin that around if you want because it's just a radius, right?
And then it would be the principal set. Okay, I got it.
This is
max.
true. And then the max shear stress.
It's a principal stress if it's sitting on the radius.
Wait. The radius is just a distance, right?
Yeah.
The radius doesn't mean much by itself. We're talking about coordinates on this circle.
So you don't even need the numbers, just need the diagram.
So at the max shear stress, there is zero axial stress acting on the element. So max shear stress would be here or here, right? But because this circle isn't centered at 0, 0,
That's not true.
it's going to be a positive number, right?
Yeah.
In the middle of the circle.
Okay.
And then the reason, you know why this is right, but like because there's no shear stress. That's the definition of principal stresses. It's where there's maximum axial stress or minimum, but there's no shear stress acting on it.
Wait, so the shear stress changes the circle by extent.
The shear stress. What do you mean? Just adding on to
Wait, okay, so in the last question, since the x and y stress was the same, right? It was both 50.
Yep.
And then
Let's go back.
And then the torque stress, the torque of both of them was 25, right? So
Wait. Be careful. So torque and shear stress are both denoted by tau, but we're not talking about torque.
Oh, well, case.
This is just shear stress, right?
Yeah. So and then you just like add in minus 25 and 50, right? Because that's like the center of the table.
But like, so it's basically the Moore circle will always sit like this, somewhere along here, right? So your tau xy and your tau, or like the negative version of it, basically, are both just going to be the radius of the circle. Always.
Yeah.
Sorry, did I answer your question? Wait, what was your question?
So no, because I'm not like so because the case is different, right? Because that's the stress in the x direction, it's the stress in the y direction. But then in the other example, the next example, they're not the same. Right.
Yep.
So then how like in what way? So like if the I forgot what the name of it. The shear stress is not zero, then what would like this diagram look like?
Oh, okay. I see what you're talking about. Basically, what is given in the question are just coordinates on the circle.
Yeah.
This circle represents any of the possible numbers that this could be as it's being rotated.
Oh, so then.
So, what would the maximum shear stress for the circle be? Like that, it could experience with these numbers.
Wouldn't it be like so if the shear stress was like 25, right? It'll be 25 from the very top of that circle.
Okay, so you're given a different set of numbers, right? Say we're given this, right? You know.
You need to try and hold it because you hold it. Okay. For what reason? For what reason? Do you think you're funny? Yeah. Do you think? Sir, did we carry it fall?
Alright, Caden.
Yeah.
These are the numbers you're given, and you plot it on the Moore circle, and it's like this. This is on the xy plane.
Okay.
So you're given the sigma x and the sigma y, right? And there's an associated shear stress of it, right? Here I've written 10. The shear stress associated with the y component, which I call yx instead of xy, is the negative version of that. So when you're given this, right? So it would be something like this, right? 10 for the shear stress.
Oh.
And then here would be like 30. That's 30, right?
So literally it's the diagram but on a circle. So
yeah.
So it's literally just graphically the shear stress is the y values. And then the x and y stresses are just completely separate coordinates.
Yep.
Oh my god.
No, but
oh, I get it now. This makes all stations central.
But tau max, right? What would tau max be?
The radius.
Yeah.
Well, in that example, will be.
In this one.
Oh, in this one. It will be. 37. Yeah.
37.5. Yeah. So you know the maximum it could be. The only reason it's given as 0 here is because these are
those points are on the rest. Oh my god!
Yeah.
All stations. All central.
And so when you're given when you're given these like funky points that aren't on here or directly like bang like vertically, right? You just do the same thing, but you have to use your circle geometry, Pythagoras for the radius.
Yeah.
The average of this and this point will mean the middle, right?
Yeah.
That's how you get the average formula.
Yeah.
Sorry, the problem was like I kind of bit off more than I could chew in terms of detail.
Yeah.
So I didn't have time to explain this properly.
Having that diagram on the top right made a lot more sense. Like seeing that it is a dot, the circle is just a dot.
Yeah.
Okay, I want to take a photo.
Yeah.
I got an upper for the circle to be honest. But I
get the diagram, the circle is a little bit harder for me.
I didn't get it up.
But it's like material sciences. If you
Yeah,
one side you don't get the
yeah,
other side.
that's actually true. Because for me, when I saw the Moore circle, it made more sense. But for you, when you saw for Josh, when you saw the that's called the shear
I
element.
think
Yeah,
that's what I like circles.
Okay.
I think
The one on the
circles are
right?
fun to work with.
Yeah, that's a stress element.
Okay.
Yep.
That's because I like circles. The circles are fun.
It's too easy.
All right. Is that the last question? That was the last question. All right. That's the end of the